So this video is a continuation of the previous one where we identified all the zero force members in the truss and also drew the free body diagram. So that has been recycled here. So this time what we're asked to do is determine the force in members CI and GH. So that's this one and this one. And state if these members are in tension or compression. So because we're asked for just two members of the truss and they're located relatively close to each other, we should be able to perform method of sections for the analysis and simplify our lives a little bit. If you were to do method of joints, you'd need to analyze a lot more joints in order to figure out just these two members that you're interested in. So I'm going to apply method of sections. Now for this we're going to need to take a cut through our structure, and this cut's going to need to separate the truss into two different parts, and we can't cut through any more than 3 unknown members, otherwise it's indeterminate and we cannot solve. So I'm going to obviously want to try and cut through the ones I need to find the force in. So we're going to try and cut through CI here and also through GH. So I can kind of map it out. So I think if I cut through like this, now this one was a zero force member, so we know that one, it doesn't count. We've now cut through one member that we don't know the force of. If I cut through this one, it's also a zero force member, so it actually doesn't count. And then I cut through this one as well. That one is unknown, so it does count. So here I've only cut through 2 unknown members, so my structure remains determinate and I'm going to be able to solve for the 2 unknowns. So this is my cut. Now we have a choice of taking the left hand side or the right hand side of our structure. I think I'm going to take the left hand side, but what that means is I'm going to have to solve for both of my reactions, AX and AY, so that I have those as being known. So let me start with that, and then we'll jump on to just looking at the left hand side. Of course, if you were to take the right hand side, you'd need to solve for EY as your unknown. Alright, so we have our equilibrium equations, and I'm going to start with summing forces in the x direction. So AX here is the only one in the x direction, so it's going to work out to be 0. So that makes it pretty easy. We now need to work out AY, and I think the easiest way to get it is to sum my moments about E. Alright, so if I sum about E, obviously EY doesn't make a contribute to the moment then, because it's acting through our point of interest. We then need to consider the 6 kilonewtons, and it's acting at a distance from E of 1.5 meters. And this is going to try and rotate this thing anti-clockwise about E, so it needs to go in as positive. The next one we have is the 6 kilonewtons. It's acting at a distance of 3 meters from E, and again it's going to try and rotate this thing in the anti-clockwise direction, so it's going to go in as positive. Alright, so I'm going to have also AY creating a moment. It's acting at a distance in here of 6 meters, the total length. And this one's going to try and rotate this thing clockwise, so it's going to go in as negative. Alright, so that's all we've got for our equation. And we can solve for AY. It comes out to be 4.5 kilonewtons. So we can mark that on the diagram. Alright, so now what we want to do is just take the left hand side of our cut. Okay. So, let's give this a go. I think that's what it's going to be. So we can mark in the 4.5 kilonewtons down here. Okay, and we're going to have some exposed forces where we've cut. So there's going to be an exposed force in here because we cut through it, and we'll call it FBC, but we already know the force in this member is 0 because it was a zero force one. Alright, we've cut through here, so we're going to have exposed it, and that's this one here. And I should mention, I'm just going to draw all of these in tension, then if they come out negative, they're going to be in compression. So this one is going to be the force in CI that we needed to determine, so we'll leave it like that for now. We've then got this one that we've cut through, and that is going to be FGI, but we've already worked out that that needs to be 0 because it was a zero force member. And then we cut through this one as well. Call it FGH. Alright, so that's our free body diagram just for the left hand side with our exposed forces. You can see that there is indeed only 2 different things that we don't know on this diagram, so it is definitely solvable. Alright, so what I'm going to need to be able to solve this properly is probably to find the angle that this force is acting at. So it's not too hard to find it. Remember that because these are 2 force members, the direction of the force is the direction of the member. So we just need to find what direction this is at. And I'm going to pull out a triangle. It's going to be this one in here. So if I draw myself a triangle, we know that the width here is 1.5 meters. And we know that the height in here is 2 meters. So this is theta. And using tan inverse of the opposite over the adjacent, we can find out that this angle is 53.13 degrees. So let me mark that in. 53.13. Alright. So we now have our equilibrium equations that we can use to solve for these 2 unknowns. I think the easiest way is probably to start with summing forces in the y direction, because then we should be able to determine FCI. Alternatively, you could sum moments about either this point or this point, and you should be able to solve for the other one. So let me scroll this down. I'm going to start with summing forces in y to be 0. So we're going to have 4.5 kilonewtons going up. This is 0 and this is 0, so they don't contribute to the equation. FGH is only in the x direction, so it's not in either. All we've got left is FCI, and it's going to be the sine side of the triangle. So if we solve for FCI, we can work out that it's going to be a negative, which means we got the direction wrong, 5.625 kilonewtons. So if it's negative, that means it's going back the other way. So when we, let's fix this up, it's going to be back this way and pushing onto the joint. So that's going to mean that it's 5.625 kilonewtons, but it's going to be in compression. Alright, so now we just need to get the other one out. And of course we can do that by summing in the x direction. It's probably the easiest way. So, in the x direction, we're going to have this going backwards. So negative 5.625 is going to be the cos component. And this one is completely in x. Alright, so we should be able to solve for it. It's going to come out to be a positive value, which means that we got the direction correct on the diagram. And it comes out to be about 3.375 kilonewtons. The direction was correct and it's pulling away from the joint, so it's going to be a tension member. Alright, so that's the 2 answers for the 2 forces that we were asked to find. Of course, if you wanted to, you could go through and solve for more. Again, you have the choice of method of sections or method of joints, depending on what you're interested in, and of course, dictates which method you pick. But that's all we were asked for, so I'm going to leave it there and look at the other videos for more examples.